Let us start discussing chemical equilibrium subjective numericals. Subjective numerical will take sulfide ion in alkaline solution. Sulfide ion in alkaline solution. Sulfide ion in alkaline solution react with the solid sulfur. React with the solid sulfur. React with the solid sulfur to form polyvalent sulfide ion. To form polyvalent sulfide ion. To form polyvalent sulfide ion. The equilibrium constant for the formation of S2 2 minus and S3 2 minus from sulfur and S2 minus ions are 1.7 and 5.3. 1.7 and 5.3 respectively. Calculate equilibrium constant. Calculate equilibrium constant for the formation of S3 2 minus from S3 2 minus from S2 2 minus and sulfur. Okay. Now S2 minus ion is taken in alkaline solution. Solid sulfur is taken. Both are reacting to form polyvalent sulfide ion. Okay. Now, which is polyvalent sulfide ion? We'll see. The equilibrium constant for the formation of S22 minus. S22 minus is one polyvalent sulfide ion, and S32 minus from one polyvalent sulfide ion from sulfur and S2 minus. That we'll see. So, sulfur plus S2 minus gives S22 minus. Okay. Sulfur and S2 sulfide forms S22 minus. For this, equilibrium constant is given. So equilibrium constant is equal to, right side we will write in the numerator. Right side we will write in the numerator. Left side we will write in the denominator. In that, this sulfur we need not write. Why? Because it is given solid. The sulfur is given solid, so that we need not write. Remaining things we will write because they are in aqueous solution. Okay. It is equal to how much given in the sense 1.7. Next, formation of this S32 minus. Formation of S32 minus from sulfur and sulfide ions. So sulfur sulfide gives S32 minus. S32 minus. For this, how to balance this one in the sense 2 times sulfur will take. Sulfide gives S32 minus. For this, equilibrium constant is equal to S32 minus by sulfide. S32 minus by sulfide. For this, equilibrium constant is how much in the sense 5.3. Equilibrium constant we have given 5.3 for this. Okay. Next, calculate equilibrium constant for the formation of S32 minus from S22 minus and S. Okay. Formation of S32 minus. Formation of S32 minus from S22 minus and sulfur. Okay. Now, sulfur and S22 minus forms what in the sense S32 minus. For this equilibrium constant we have to find. Okay, sir. Now we want this required equation. For this required equation, S22 minus is given. S22 minus we can get from this first equation. So let us reverse the first equation. Okay, so we are reversing the first equation. On reversing the first equation, what we will get? S2 2 minus aqueous gives S2 minus aqueous plus sulfur solid. For this, we will write Kc, that is equal to right side in the numerator. We are writing right side in the numerator and left side in the denominator. Left side in the denominator we will write. Okay. Now you see this reaction Kc you see, and you see this one. Okay, this Kc you see. This Kc, and just now we have written that Kc you see how it is there, both reactions, how it is there you see. In this Kc S2 2 minus numerator. Okay. Now in this case S2 2 minus in the denominator. So here S2 2 minus in the numerator, just now we have written that is in that S2 2 minus in the denominator. That means if you reverse this, you will get just now written. So we have to reverse this. So reverse this. So if 1.7 reversing means it will become what? 1 by 1.7. Okay. Sir. Next we will see. Next this we will take. Okay. Now we want S32 minus in the right side. In the required equation, S32 minus we want in the right side. That is available in the second equation. Okay, take second equation as it is. So what is that second equation? 2 sulfur plus sulfide gives S32 minus. Okay, Kc is 5.3. That we will take. So 2 sulfur plus sulfide gives S32 minus. For this Kc, is equal to 5.3 given. Okay, we have taken as it is. Correct? We have taken as it is. Okay, sir. So we have taken this equation as it is. We have taken, so Kc we have taken as it is. Okay, 5.3. Now let us add. Let us add these two. Now what are the getting cancelled? That you cancel it. One sulfur is getting cancelled. So remaining one sulfur will be there. Then this sulfide is getting cancelled. This S2 2 minus gives S3 2 minus. For this equilibrium constant is equal to what we can say in the sense. Okay. So now we will write this one. Right side in the numerator we will write S3 2 minus. Left side we will write in the denominator. In that sulfur we need not write because that is solid. For this case we will write right side in the numerator, left side in the denominator. Okay. Now we want Kc for the required equation. For this reaction we know Kc. For this reaction we know Kc. Using these two Kc, how to get this Kc? Okay. So now you take this one, you take this one, multiply these two. Multiply these two. What you are getting, you see, multiply these two. Do you get this? Then we can multiply these two Kc in order to get this Kc, we can say. So we are multiplying these two Kc. Okay. So we are multiplying these two in order to get this Kc. We are multiplying these two Kc values in order to get this Kc value. So these two we are multiplying. Okay. So we got this much. So we got the Kc value we got. That is how much in the sense 3.11. Okay. So required equilibrium constant we have found it. Let us take next question. To 500 ml of 0.15 m to 500 ml of 0.15 m silver nitrate solution were added 500 ml of 1.09 500 ml of 1.09 m Fe2 plus solution and the reaction is allowed to reach and equilibrium at 25 degrees Celsius. And equilibrium at 25 degrees Celsius. Ag plus aqueous plus Fe2 plus aqueous gives Fe3 plus aqueous gives Ag solid. For 25 ml of the solution, 30 ml of the solution, 30 ml of 0.0832 molar K-monophore were required for oxidation. Calculate equilibrium constant. For the reaction. Calculate equilibrium constant for the reaction at 25 degrees Celsius. Calculate equilibrium constant for the reaction at 25 degrees Celsius. Okay, sir. Now silver nitrate is given. How much silver nitrate given? We will see. So silver nitrate is given how much in the sense 500 ml 0.15. Okay. So silver nitrate is given how much in the sense 500 ml, that we will multiply with 0.15 molar. So what we will get in the sense, we will get millimoles of silver nitrate. Volume of solution in milliliter and molarity we have multiplied, we got millimoles of silver nitrate we got. From this we can say how much Ag plus ions in the sense 75 millimoles of Ag plus ions and 75 millimoles of NO3 minus ions. Ag plus ions 75 millimole, NO3 minus ions 75 millimoles. Okay, next given is ferrous ions. Ferrous ions how much we will see? Ferrous ions how much we are seeing? That is 500 ml of 1.09 molar ferrous ions. 500 ml of 1.09 molar Fe2 plus ions. Okay, how much volume means 500 ml, and what is the concentration in the sense 1.09? We are multiplying these two, we are getting a 545 millimoles. 545 millimoles of Fe2 plus ions we are getting. Okay, let us take this for reaction. We are taking this for reaction. That means we are mixing this Ag plus aqueous and Fe2 plus aqueous. Ag plus aqueous and Fe2 plus aqueous we are mixing. Fe2 plus is converting into Fe3 plus aqueous. Ag plus aqueous is converting into Ag solid. Ag plus aqueous is converting into Ag solid, we are saying. Okay. So initially how much Ag plus we have taken? 75 millimoles. How much Fe2 plus we have taken? 545 millimoles. How much Fe2 plus we have taken? 545 millimoles. Okay. How much reacting? That we will see. How much is going for reacting? So why we have to see how much is going for reaction? Because they are asking us to find equilibrium constant for this reaction. For this reaction, they are asking us to find equilibrium constant. So we have to find equilibrium constant for this. Okay. So we want equilibrium constant in the sense we want equilibrium concentrations of these ions. So how much reacting we have to see. How much reacting, any clue is given or not, that we'll see. How much is reacting, any clue is given or not, we'll see. Okay. First what they said, what they did, the silver nitrate and ferrous, they mixed and allowed this one for equilibrium. Okay, this they allowed for equilibrium. For this what we have to find? Kc we have to find. For this reaction we have to find Kc. If we want Kc, we want equilibrium concentrations of these ions. Equilibrium concentrations of these ions we want. For that any clue is given or not, we'll see. For 25 ml of the solution, 30 ml of 0.0832 molar K-monophore were required. 25 ml of which solution? This equilibrium solution. This equilibrium solution they have taken 25 ml. This 25 ml of this equilibrium solution requiring this much potassium permanganate. So why they have given this clue? What is the reason? That we will see. Okay, for which we will take this potassium permanganate. We are taking this potassium permanganate. In this potassium permanganate, this potassium comes under group number 1. Therefore, it is having charge plus 1. Potassium coming under group number 1. Therefore, it is having charge plus 1. Group number 1 in the sense periodic table group number 1. Valence is 1. Okay. Then manganese is there and oxygen is there. This oxygen is called oxide. This oxygen is called oxide. For oxide, charge is 2 minus. Charge is 2 minus. That means this charge is 2 minus in the sense it is having noble gas configuration, neon configuration. This K plus is having noble gas configuration, argon configuration. That means it is stable, it is also stable. Regarding manganese, we will see. Regarding manganese, atomic number of manganese is 25. Therefore, electronic configuration is argon 3d5 4s2 is the electronic configuration of manganese. Here, manganese is having how much charge? How much charge in the sense that we will calculate. What is the charge possessed by manganese? For which we will take this potassium. Potassium is having plus 1 charge, we know. Potassium is having plus 1 because group number 1. Manganese charge we want, therefore that is X. Oxygen how much means 4 times. Each oxygen is having how much charge means minus 2. Net charge is 0. Because over K1O4 we are not writing any minus or plus. It is not ion. It is not cation or anion. Therefore, net charge is 0. From this, we can find X. X is equal to how much in the sense plus 7. So, manganese is having what charge in the sense plus 7 charge it is having. Okay. So, now we will convert this manganese into plus 7. Manganese plus 7 in the sense the configuration is argon 3d0 4s0. Why? In order to convert manganese into plus 7, we have to remove 7 electrons from manganese. How to remove 7 electrons? First remove 2 electrons from 4s, then remove 5 electrons from 3d. So totally 7 electrons removed. So M1 plus 7 is having so and so configuration. Now, this M1 plus 7 can't donate any more electrons. M1 plus 7 cannot donate any more electrons. Why? Because it has got argon configuration, stable configuration. But it can accept electrons. It can accept electrons means it can go for reduction. These possibilities there. It cannot donate electrons because donating from argon is not possible. Therefore, it cannot donate electrons. Therefore, it cannot undergo oxidation. It never undergoes oxidation, but it can undergo reduction. It may gain electrons. Therefore, K1O4 can, in the K1O4, manganese can undergo reduction. Sir. Next, what are the other species given in the question in the sense? Another one is iron. Iron atomic number is 26. Its electronic configuration is argon 3d6 4s2. Iron electronic configuration is argon 3d6 4s2. Now we will write Fe2 plus we will take. Fe2 plus in the sense you have to remove 2 electrons from this. Which 2 electrons let us remove? Highest energy shell, outermost shell, valence shell. Highest energy in the valence shell is 4s. So remove 2 electrons from 4s. Therefore, we are getting configuration argon 3d6 4s0. Next, we will take Fe3 plus. Fe3 plus we will take. Fe3 plus means, so from Fe2 plus, we have to remove 1 electron. Then only we will get Fe3 plus. In this Fe2 plus, we have to remove 1 electron, then only we will get Fe3 plus. So which electron we have to remove? From 3d you remove it. Okay. So that argon 3d5 4s0. Argon 3d5 4s0. It is Fe3 plus. So Fe3 plus configuration is what in the sense? Argon 3d5 4s0. Okay. 3d5 configuration. 3d5 means off-filled configuration because d subshells are 5. D subshell contains 5 d orbitals. So for each orbital 1 electron if we fill also it is off-filled configuration, but it is partially filled configuration. 3d6 is partially filled configuration, 3d5 is off-filled configuration. Therefore, Fe3 plus is stable, Fe2 plus is less stable. Fe2 plus is having less stability, Fe3 plus is having more stability. For that, what is the evidence? Now, ferric salts is there in the laboratory. In the school laboratory, ferric salts are there. Ferric salts, suppose we are purchasing now. You can leave this ferric salts in the number of years, 1 year, 2 years, like this, you leave it. After 2 years also, you see there is no change in the ferric salts. But what about ferrous salts? Ferrous salts, take some amount in the watch glass. Take some amount of ferrous salts and expose to air. Within few seconds, ferrous will convert into ferric. This ferrous salts exposed to atmospheric air for few seconds. Within few seconds, this ferrous is converting into ferric. Okay. Therefore, shall we say it is having less stability? Ferrous is having less stability, whereas ferric is having more stability. Okay. That means ferrous easily converting into ferric. Ferrous easily converting into ferric. +2 is converting into +3 in the sense loss of one electron. Therefore, it is called oxidation. So, ferrous can undergo oxidation. But ferric is stable. Ferrous can undergo oxidation easily. Okay. So, one thing we have said, manganese can undergo reduction, we said. Ferrous can undergo oxidation, we said. Then regarding silver. Regarding silver, you know that silver ornaments, you know. Silver ornaments we are purchasing, we are using for a number of years. That means, is it losing its luster immediately? Is it losing its brightness, luster immediately? No. That means it is not participating in the chemical reaction easily. It is not involving in the chemical reaction with atmospheric oxygen. Therefore, Ag into Ag plus is not easy. It's not easy. Silver is not involving in chemical reaction easily. Correct? So that silver is not involving in chemical reaction easily. That we know that. Okay. Now we will take this equation. Okay. Now this is the equilibrium reaction given. In this question, this is the equilibrium reaction given. This equilibrium solution is taken 25 ml. We are taking this equilibrium solution 25 ml we are taking. This equilibrium solution, how much we have taken means 25 ml we have taken. This equilibrium solution is taken for titration with this K-monophore. This equilibrium solution 25 ml is taken. It is taken for reaction with this potassium permanganate. Okay. Now you say, in the potassium permanganate, we said this manganese can undergo reduction. Now Fe3 plus in the now Ag is there. Ag, this manganese can undergo reduction, we said. Okay, manganese can undergo reduction. Then Ag, silver cannot undergo oxidation easily, we said. So regarding silver, leave it. So K-monophore reaction with the silver we can leave. It is undergoing reduction means another should undergo oxidation, isn't it? Okay. One is undergoing reduction means another must undergo oxidation. Which can undergo oxidation? That's what we have to find it. Silver can't undergo oxidation under the given condition. They also said K-monophore is required for oxidation, they said. So which will undergo oxidation? Which species will undergo oxidation? Regarding Fe3 plus, it is stable, we said. Fe2 plus, we said it can undergo oxidation. Okay. So Fe2 plus can undergo oxidation, we said. Therefore, there is the possibility of reaction between potassium permanganate and ferrous. Then Ag plus we will take. Ag plus, silver can show +1 oxidation state but not other. That means can't silver show other oxidation state? Yes, of course it is showing. It shows +2, but which is most stable in the sense Ag plus. Most of the silver salts in the industry and laboratory, in that silver shows +1. Most of the complex salts in which silver shows +1. Therefore, silver is not undergoing oxidation under the given condition, we concluded. Therefore, which is undergoing oxidation, which is undergoing reduction in the sense Fe2 plus can undergo oxidation, K-monophore can undergo reduction, that is a reaction. So, this equilibrium solution you are taking 25 ml. In that solution, which is undergoing reaction in the sense K-monophore and Fe2 plus undergoing reaction. Okay. What is that reaction that we will see? So KMnO4 and Fe2 plus undergoes reaction. Okay, that we got an idea. Okay, so now KMnO4 will take KMnO4 in that permanganate we have taken, Fe2 plus we have taken, they are going for reaction. They are going for reaction. Okay, so here permanganate will convert into what? It is undergoing reduction means it is converting into what? It is converting into Mn plus 2. Fe2 plus is converting into Fe3 plus. Okay, Fe2 plus is converting into Fe3 plus. Permanganate is converting into Mn plus 2. Permanganate is converting into Mn plus 2. Fe plus 2 is converting into Fe plus 3. Okay, sir. Now we have to balance this. How to balance this? That we will see. In the permanganate, manganese is plus 7, in the Mn plus 2. Plus 7 is converting into plus 2 in the sense gain of 5 electrons. Gain of 5 electrons. Then Fe plus 2 is converting into Fe plus 3 in the sense loss of 1 electron. Now make gain of electrons and loss of electrons equal. Therefore, what we have to do? Multiply this with 5, multiply this with 1. So loss of electrons becoming 5, gain of electrons becoming 5. Therefore, take 5 Fe2 plus and 5 Fe3 plus. Okay. If you take 5 Fe2 plus converting into 5 Fe3 plus, then loss is equal to 5 electrons, then loss and gain equal. Okay. Then oxygen here 4. Therefore, write 4 water molecules. Hydrogen 8. Therefore, write 8H plus. Okay. Now we have balanced. Now let us see charge. If charge is balanced, then we can say equation is balanced, we can say. Now let us balance the charge. We will see not balancing. We have to see whether charge is balanced or not. We have to see. Here charge is, in the permanganate charge is -1. In the ferrous 5 into 2 plus 10. 5 into plus 10. Here in hydrogen 8 into plus 1 8. Therefore plus 17. Here charge is plus 17 left side. Right side we will see. Manganese plus 2. Iron 5 into 3 plus 15. Therefore plus 17. Charge is balanced means equation is balanced. Okay. Now for this reaction, now equation is balanced, we said. Now what is the formula? Now how to find how the, for what sake they have given this, that we'll see. Okay. Now we can say 1 millimole of permanganate, 1 millimole of permanganate reacts with 5 millimoles of ferrous ions, we can say. As per the reaction, as per the balanced equation, we can say 1 millimole of permanganate reacts with 5 millimoles of ferrous ions, we can say. Now we will see in the question how many millimoles of permanganate is given. We'll see. Permanganate how much given? Permanganate given 30 ml of 0.0832 molar. That means we'll write what is potassium permanganate given in the sense 30 ml into 0.0832 molar. Okay. Potassium permanganate how much given in the sense 30 ml into 0.0832 molar is given. On multiplying these two, we are getting millimoles of potassium permanganate. So how much millimoles of potassium permanganate given in the sense 30 into 0.0832 millimoles of potassium permanganate given. Okay. So now we will take that. So potassium permanganate how much given in the sense 30 into 0.0832 millimoles given. This many millimoles of permanganate will react with how many millimoles of ferrous ions, that we will see. Okay. So we will find millimoles of ferrous ions, we will find. Okay. So we are getting millimoles of ferrous ions, that is equal to 5 into 30 into 0.0832 by what? Okay. This many millimoles of ferrous ions we can say. So we got ferrous ions millimoles, we got ferrous ions millimoles. This much millimoles of ferrous ions present at where? This much millimoles of ferrous ions. This much millimoles of ferrous ions present in which solution? Which solution means 25 ml of this equilibrium solution. 25 ml of this equilibrium solution contains that many millimoles of ferrous ions. Okay. So we can say that 25 ml of this solution, 25 ml of this solution contains that much. So 25 ml of this solution contains that much we are saying. Okay. So we said 25 ml of equilibrium solution contains 5 into 30 into 0.0832 millimoles of Fe2 plus ions. Okay, sir. So Fe2 plus ions how much present in the equilibrium solution that we got. Okay. Now here how much, so here we will see now this one we'll see. Ag plus how many ions we have taken? Ag plus solution is how much? 500 ml. Okay, 500 ml of Ag plus solution. Then Fe2 plus ions how much? 500 ml. Fe2 plus how much? 500 ml. That means you have taken Ag plus solution 500 ml. Fe2 plus solution you have taken 500 ml. That means totally how much solution you have taken? 1000 ml you have taken. You have taken 1000 ml of solution. Therefore, initially we have taken how much solution? 1000 ml of solution you have taken. Sir, at equilibrium also 1000 ml of solution only will be there, no? Okay, even at equilibrium 1000 ml of solution will be there or not? Of course, instead of Ag plus Ag will be there like this, but 1000 ml of solution will be there, isn't it, sir? So at equilibrium how much is there means 1000 ml of solution is there. So 1000 ml of solution contains how much Fe2 plus ions that we have to see. But 25 ml of solution contains this many millimoles of Fe2 plus ions. So 1000 ml of solution contains how many millimoles of Fe2 plus ions that we have to see. Okay, that is equal to 5 into 30 into 1000 we have to multiply. So 1, 2, 3. Therefore 83.2 millimoles of Fe2 plus ions. Okay, so this many millimoles of Fe2 plus ions present at 1000 ml of equilibrium solution. So equilibrium solution contains how many millimoles of Fe2 plus ions that we got an idea. Okay, sir, this on simplification how much we are getting in the sense that is so 499.2. So this many millimoles of Fe2 plus ions are there. Okay, sir. So now we got at equilibrium how many millimoles of Fe2 plus ions are there. We got an idea. That is how much in the sense 499.2 millimoles of Fe2 plus ions present. At equilibrium, how much Fe2 plus ions present in the sense 499.2 millimoles present. How much Fe2 plus ions we have taken initially? 545. 545 millimoles of Fe2 plus ions we have taken initially. At equilibrium this much remaining. So how much reacted? How much reacted in the sense 45.8 millimoles of Fe2 plus ions reacted. So Ag plus will react how much? Same 45.8. So how much Ag plus will be remaining? Okay, how much Ag plus 75 minus 45.8 millimoles of Ag plus ions remaining. Okay, then Fe3 plus. How much Ag plus reacting, that much Fe3 plus will be forming. So Fe3 plus will be formed, 45.8 millimole will be formed. Ag plus is solid, so we need not consider. If you want also, we can write 45.8 millimole. Okay. Now we want equilibrium constant for this reaction. That's what they asked us to find. So equilibrium constant is equal to concentration of Fe3 plus in the numerator, because that is there in the right side. In the denominator, we can write left side thing, that is Ag plus, and Fe2 plus we can write. Okay, concentrations we can write. Now we are substituting. We are substituting how much. What is the concentration of Fe3 plus means 45.8 millimole, and volume of the solution is 1000 ml. That 1000 ml we will substitute. So we got concentration of Fe3 plus. Then Ag plus we will substitute. That is 75 minus 45.8. It is millimoles of Ag plus by 1000 millimoles. It is the concentration of Ag plus. Then Fe2 plus we will substitute. Fe2 plus how much in the sense Fe2 plus is 499.2 millimoles of Fe2 plus present at equilibrium. Volume of solution is 1000 ml. 1000 ml, we got a concentration of Fe2 plus. We are simplifying, we are getting equilibrium constant, that is 3.142. Okay, so we got a equilibrium constant for this reaction set. So we got equilibrium constant that we have found. Okay, let us go for next sum. Let us go to next sum now. For gaseous reaction, for gaseous reaction, A plus B gives C, A plus B gives C. The equilibrium concentration of A and B, the equilibrium concentration of A and B at a temperature or at a given temperature, at a given temperature or 15 molar or 15 molar. When volume is doubled, when volume is doubled, when volume is doubled, the reaction has equilibrium concentration, the reaction has equilibrium concentration, the reaction has equilibrium concentration of A as 10 molar, of A as 10 molar. Calculate Kc, calculate Kc. Second subdivision, concentration of C, concentration of C in original equilibrium, concentration of C in original equilibrium, concentration of C in original equilibrium. Okay, so in the question given data we will see, they have given a equation that is A plus B gives C, A plus B gives C. Okay, equilibrium concentration of A and B 15 molar. Okay, equilibrium concentration of A and B given. Okay, it is 15 molar, it is 15 molar. Okay, equilibrium concentration is given. Okay, now when volume is doubled, the reaction has equilibrium concentration A 10 molar. Okay, now we are doubling the volume, therefore new equilibrium is attained. In new equilibrium A is 10 molar. Okay, so A plus B gives C. A is 10 molar in new equilibrium. Okay, what is Kc? Okay, now we have to find Kc. So Kc will take, Kc is equal to concentration of C by concentration of A into concentration of B. Here also we will take Kc. Kc is equal to concentration of C by concentration of A into concentration of B. It is new equilibrium. It is old equilibrium. Okay, now here Kc and here Kc will be equal. Here Kc and here Kc will be equal, sir, because same reaction, nature is same. Only thing we are giving the stress, that's all. We are giving the stress in terms of what? Doubling the volume. Okay, sir. So now we know that here Kc and here Kc is same. Okay, we know A and B concentrations. If we know C concentration, if we know concentration of C, then we can find Kc. So how to find C? Sir, how to find C? We are having doubt, sir. For which what we have to do means we are doubling the volume, sir. Due to doubling the volume, what will happen to this concentration? Becomes off, isn't it? On doubling the volume, concentration becomes off, because concentration is inversely proportional to volume. So you are doubling the volume means concentration becomes off. Therefore this concentration becomes how much in the sense, that concentration becomes how much in the sense 7.5 molar. It is also 7.5 molar. Okay, this 15 molar becomes 7.5 molar, but the system is not at equilibrium now because we disturbed, we gave the stress, correct? So that system will go for what we have to see. Now see, 10 molar, now new equilibrium 10 molar in the sense backward is favored or forward is favored? Backward is favored, isn't it? So backward is favored. Concentration of C we do not know, suppose X, therefore we will write here X by 2. Now backward is favored how much extent? Backward is favored how much extent means such that here plus 2.5 molar, isn't it?